contents are from a book by Rao V. Dukipati or Dukipati, MATLAB, An Introduction with Applications. It's a really nice book. If you people can procure it, can lay your hand upon it, you should consider going through this one for nice practical applications of MATLAB in mechanical engineering domain. Now, the outline of today's presentation will be something like this. I'll quickly try to cover this engineering mechanics and SFD BMD concepts very quickly. Many of you might remember it really well. So for them, it might be a little boring. Please bear with me. Then I will move on to case studies in engineering mechanics, case studies in shear force and bending moment diagrams for the beams, and then more circle one case study. Case study means what? Obviously, the numericals that we deal with in our courses. I'm sure many of you are faculty, working as faculty. So you would be dealing with your courses. So our focus is to deal with the course content and delivering the course content using MATLAB. So that's the idea. So the first topic will only be presentation oriented. The other topics are all hands-on or demonstration oriented. So let me just get started. Okay, so Newtonian mechanics, the study of statics and dynamics is called classical mechanics. Please excuse me, there is one expression that is, 1 second. Okay, no problem. Then it is also called as Newtonian mechanics. We have first law, which is related to inertia. Then we have second law, which is related to change in momentum being directly proportional to the applied force. F equals to ma is the standard expression. Here it has been written in terms of F or M, just for the just to show the importance of our need to find out acceleration provided we have F and M. And third law, of course, famous, says for every action there is an equal and opposite reaction. Okay. Then we have coplanar and non-coplanar force systems. This is what we generally use in engineering mechanics. Most of our engineering mechanics problems deal with this. So if you have non-concurrent, non-parallel system, that is planar system, then you will have a resultant, and then you will have the inclination of resultant with respect to either one of the forces. So they are given by the respective formulae. And then you have non-coplanar force systems, that is neither concurrent nor parallel. Then you will have a 3D force system, which will have summation of all forces along x squared plus summation of all forces along y squared plus summation of all forces along z squared, the whole under root as the resultant, and the corresponding angles of the resultant. Okay, so the standard stuff. Most of you, if not all of you, would definitely remember this. Just to give you a quick recollection of these things, I'm just going through this one. And of course, the necessary and sufficient conditions required for equilibrium for both concurrent and non-concurrent, for both coplanar and non-coplanar systems are, we sum up forces along x, y, and z directions and equate them to 0. And then also we take moments about a particular point along a particular direction and equate it to 0 for equilibrium, right? So this is the standard stuff. Okay, again, the same issue. Please excuse me. I'll just. Okay, friction, we know that it is nothing but tangential force between surfaces of two bodies that opposes the sliding of one body relative to other, and it is known as the status friction between the two bodies. Kinetic friction is nothing but tangential force when one of the body is in motion or both bodies are in motion, and the body only begins to slide when the applied force exceeds the static frictional force at the floor. Floor here means the resting ground. Then limiting friction F dash is nothing but the maximum value of static friction that occurs when motion is impending. Then coefficient of static friction is the ratio of limiting friction F dash to the normal force N. And coefficient of kinetic friction is the ratio of kinetic friction to the normal force. Right? Oh, sorry. I think I have not taken care of this presentation. Anyway, so an angle of repose is nothing but we saw in the previous sketch the angle with which the plane is inclined. That is what is the angle of repose. A simple application of this friction which we as mechanical engineers generally use is this belt friction, wherein a belt passes over a pulley, and the tensions between difference in the tensions between the sides of the belt run the pulley, and it is we know it very it is given as T1 by T2 equals T power mu b, where T1, T2, mu and b are as given. Okay, so this is the friction. Beams, we know beam is a long member. Long in the sense length is much more than the cross sectional dimensions, which is subjected to external lateral forces F and external lateral moments M. Now there are different types of supports: simple support, roller support, hinged and fixed support, and they offer the reactions that are mentioned in the corresponding bracket terms. And there are different types of beams based on the types of supports and the type of the supports at the ends of the beam. So you have a cantilever beam, simply supported beam, overhanging and fixed beam. There are other types of also, but generally these are the majority of the types of the beams. Then general, most usually encountered types of loads: concentrated load, uniformly distributed load, UVL, and externally applied moments, right? I'm sorry. Okay. So sign conventions, this is somewhat important. I'll just spend a little bit of time here. So when you have a force that is causing, what we do is generally in a beam, we imagine a cutting plane. We imagine that the beam is cut off at a particular point along the length of the beam, and we try to analyze shear force and bending moment at that particular point. So generally, universally, the convention that is taken is, if a force causes the left portion of the beam to move up in the sense, again, these are all imaginary happenings. So if it causes it to move up, then that sort of a force is called as, or is taken as positive. And on the contrary, if the left portion of the beam, of the cut portion of the beam, moves down, that is what is considered as negative shear force. Similarly, bending moment, if the bending moment causes sagging in the beam, then it is called as or then is taken as positive bending moment. Sagging, again, when the beam bends downwards, that is the sagging bending moment. Somebody's transverse loads, yes. Thank you, Chandramohan sir. That's actually transverse loads. Lateral is taken in that sense only. Thanks for correcting me. So then sagging bending moment, when you take left side of a particular cut portion, sagging bending moment translates to clockwise, and that is clockwise bending moment is positive, and negative bending moment would be anti-clockwise on the left hand side of the cut portion. So this is the general conventions that are universally taken. Sorry. And we know a very famous relationship between the load intensity, shear force, and bending moment. So dF by dx is given as W, that where W is the load intensity. dm by dx is given as minus F. It depends. The minus is sometimes in some of the literature you'll find dF by dx as minus W and dm by dx as F, and vice versa, what I have shown here. So both ways it is okay. What we are interested in is the absolute relationship between the corresponding terms. Okay, so let's quickly also have a look at Morse circle. Now, before we go to Morse circle, we need to know that what are compound stresses. Basically, when any body is subjected to multitude of stresses in different directions, then we call the stresses induced within the member as compound stresses. And we generally take universally applicable thing is a three-dimensional stress element, or a stress tensor element, what is called a stress tensor element, which is seen on the left hand side. But most of the problems we try to simplify it and say it is a plane stress element. So if a plane stress element is loaded as shown in the right side figure. So we are generally interested in finding out the normal stress and tangential stress on a plane inclined at some angle theta within this particular compound loaded element. So with that, we try to go ahead. So when you take that, okay, so this is the, I've put all the formula in one go so that we don't have to scroll too much. So we have the normal stress on a plane. Here again, the notations may differ. Many of you might be using sigma x, sigma y, and tau. In other literature, you would be seeing usage of P and Q. So I am sure you would be okay with any of these conventions, as long as you don't get confused. So from the source from where I took it, it was mentioned in this way. So I just to minimize my effort, I have just used the same symbols. So normal stress on the inclined plane is given as px plus py by 2 plus px minus py by 2 cos 2 theta plus q sin 2 theta, and tangential stress is px minus py by 2 sin 2 theta minus q cos 2 theta. So when we know there exists a plane on which there will be no tangential stress, that sort of a plane is called as principal plane. And on the principal plane, whatever stresses, normal stresses occur, they are known as principal stresses, given by P1 and P2 with these formulae. So P1 and P2 together, you can say it as Px plus Py by 2 plus or minus root of Px minus Py by 2 whole square plus Q square. And tau max, or rather, sorry, Pt max, that is tangential stress, also there is a plane where it will be maximum. That is given by differentiating the expression for Pt with respect to theta and equating it to 0, that is maximizing the Pt. So if you do that, you will get a inclination, a plane inclination, which you substitute back, you will get it as Pt max equals to root of Px minus Py Py by 2 whole square plus Q square. Now coming to the Mohr circle, this is the point where we will be dealing with in today's discussion. So a Mohr circle is nothing but a circle. It was given by Otto Mohr, the famous Otto Mohr, and he gave us this idea that a circle with its center at px plus py by 2 and radius as root of px minus py by 2 whole square plus q square, which is nothing but the Pt max, in a Cartesian coordinate system with direct stresses along one axis and shearing stresses on another on the other axis, along the other axis, is what is called as a Mohr circle. You can see an indicative figure in this particular slide here. So this is what is the Mohr circle, which we get by plotting various points. Now we will take up an example to obtain this Mohr circle. So now with that, I end my presentation. So this is just quick theoretical recollection. I cannot afford to spend too much time on this particular this one. So I will just now switch over. What I'm planning to do is I want to avoid this switching between the windows. I think since these 3 days, you people have seen that we often keep switching between the windows. Probably that causes a sort of distraction or loss of focus. So what I'm planning is I'll just stick to one window, that is MATLAB window, where I'm going to show you all the case studies. Okay. So as I told you, case studies are nothing but are regular numerical problems, analytical problems that we deal with in the course of in the courses of engineering mechanics and strength of materials. Hello, Vaishnavi Sundar, are you addressing me or?
I'll mute her. She is muted.
Okay, fine. Okay, so you might be wondering, if I directly go to this MATLAB window, how can I show you the what do you say, the problems or the statement of problems? So for that, I have one a novel way of taking care of that. Till now, you people would have you would have seen usage of scripts, right? In the past 2 days, since you were introduced to script, we saw how script can be used for creating MATLAB programs. I now introduce one other concept called live script. Okay, it's a very interesting way MATLAB shows you things. This is a thing wherein we can include active content, not active content, a content such that it is having some text and graphic part of it. So what I'll do is I have uh, opened up this MLX. It is called as live script is having an extension .mlx, and I will now, sorry, excuse me. I will now paste the problem statement here. I have gone in text mode. You can see here there is a text mode, there is a code mode. So if you do text mode, you can do simply copy paste. Okay, I'll just reduce the size here. I hope you people are able to see the question.
Yes,
I have
yes,
reduced the
yes.
size, but I hope it is readable. Okay, and let me paste the figure, corresponding figure, which is okay, I'll reduce this also. Yeah, good enough. So I'll give you a minute's time to read this question. Very simple, basic question. I'll just try to deal with simple things in the beginning so that it is easier to move towards more bigger things. So now I am in text. I have chosen text mode, as you can see. Now I'll just, okay, before I do anything, I have to also show you some of the things that I want to show. We will start saving this. So let me save this particular thing. Let me just make it simple. I'll say engineering mechanics case study 1. Right. So this is the okay. The right side window that you see is where the actual output of the code will be shown. Okay. And sometimes if we are plotting, the graph also will be shown on the right side. We'll see when we. Now for this one, I think it's pretty very simple. So I'll just give you the formulae. I mean, I need not, but I'm just trying to be more methodic in nature. So your resultant along the x direction will be summation of force, summation of all the forces, or rather summation of force into cos of the inclination of the force with respect to the x direction, and that will be your x component or x resultant, and similarly your y resultant will be this one. Okay, and it's pretty simple. I'll just okay, and alpha or theta or whatever, whichever notation you use, the understanding is the same. So is this one, right? So we have to, all we have to do is we have to just code these particular formulae. I think yesterday when you were there in first session, Trupti ma'am, when she showed you, this is what we all do. I mean, we have a set of known relations or known equations, and we have to just type in code, key in code for all those expressions or relations or equations, whatever you call. Okay, now I'll go into this code. I'll just see. I'll just click on this particular code. So now I'm ready to do the coding. Now I think okay. So I suggest you just note down these values somewhere. F1 is 20 kilonewton, F2 is 40 kilonewton, F3 is 200 kilonewton, alpha 1 is 40 degree, alpha 2 25, alpha 3 is 58, right? So these are all the things. So we need to code. Now, actually, if you speak, there is nothing big deal in this code. It is very, very simple, but I'll try to make it a little bit more interesting. I'll taking a cue from yesterday's Trupti ma'am session. What I'll do is I'll type out the code individually. For this one example, I'll not share the code on the chat window. For the others, I'll just share the code. For this one, I'll type out. I request you people also to follow along with me, especially if you are doing. Okay. Okay. So I'll just a good practice is to clear off the screen as well as the data content, so that whatever previously run things are there, they can be cleared away. So I'll just do that. Then what I'll do is rather than just writing a code.
Excuse me, Narayani sir, excuse me.
Yeah, yeah.
Sir, how you are getting that command window there? Means that script you are getting, no? And you open that.
Yeah.
Yeah, this. So for that you have to take some option, or it will come directly. Yeah, when you do that new script.
If you are also trying to code along with me, you need not bother going into this live script, because you will not copy paste these things, isn't it? I am copy pasting the question, figure, the formula, everything here. So I need this. You may just go to new script and do this whole scripting in the script, normal script itself.
Okay. Okay.
Yeah. Yeah. I'm just showing you this option so that you people can use whenever you want. Maybe in your own classroom session.
I try to open the same that new live script.
Okay. Okay.
Here I am not getting this.
Okay, you need not. You can just go to new script itself. Just click on new script and start typing this code.
Yeah.
You need not bother to go in live script only. All this code will work in exactly same way in new script, in normal script also, .m file also. Okay. This is just for me to show you people.
Yeah, thank you.
Yeah. Right. So now there are two things that can be done with this question now. Now I can just simply try to solve this question by taking these F1, F2, F3 alpha and all, and get it. That's one way. The other way is to make it more interactive, make it more user interactive, so that user can give us the values, the data and all, and we can, so it becomes more generic code. Okay, a code which can be applied for n number of forces, not necessarily just these three given forces and these three given angles. So to take care of such a thing, what I will do is, yesterday you people saw this input function. So I'll make use of this input thing here. So before that, okay, enter the number of forces in the system. Okay, so I'll do this so that I get to get to know how many forces are there totally, which we have to take care of. Okay, then I will for this Rx, okay, let me not use this sum. I'll say Rx, okay, equals to 0. I'll initialize this Rx, that is resultant along x direction. I'll initialize it to 0. So let me just give some comment here. X-axis Ry equals to 0. I will copy paste this. Again, commenting, you people can, maybe you can avoid right now. Commenting is a very good practice, coding practice. You people should comment your code. But right now, if you are following along with me and if your typing is little slow, then you may just skip this commenting part. You can just go ahead with the coding part alone. Okay. Then I will also create 2 vectors. Okay, what is the logic here? Let me tell you the logic. The logic is I will take the number of forces. In this case, it is 3 from the user, and for how many ever forces are for this n, I will go in a loop I'll iteratively keep asking the user, enter force number 1. If the user says 3 forces, I'll say enter force number 1, enter force number 2, enter force number 3. Then for the force, I'll have to take alpha. So I'll say enter alpha for force 1, enter alpha for. So like that, I'll keep taking input from the users, and then I will try to do the calculation. So for that, I'll require a set of forces. So I will initialize the forces, or I will say forces is too much. I'll just say F. Okay, F equals to. I'll initialize it. I'll make it zeros of 1 comma n. Okay, I've taken one row vector. Okay, which is already initialized to zeros. Similarly, I will also take one alpha or angles. Okay, I will take angle, which also will be of same size, right? I will initialize these things. So I have initialized. Why am I initializing? Because I want it to start with default 0 value, so that we can keep adding. Okay. Now let me give comment here also. Force vector. This is angle. Sorry, not angel. Angle vector. Right. Now I will start one for loop. I think you people got introduced to this for loop day before yesterday itself, but I'm not sure whether you people used anywhere. So here I am just trying to use it for this one. So I'll take one variable. You people would be aware of this from your programming course, which you would have taken during your engineering degree. But maybe if you may or may not remember, so I'm just telling you. So what it does is for I equals to 1 to n. That means we know what is this 1 to n. 1 to n will give you a vector with starting from 1 as the initial value till the n by incrementing default by value of 1, right? So it will go here. So this live script, one advantage is if you type code, it will try to autocomplete. So if I wrote for, it automatically wrote and it auto-populated end. It's a little smart way of lazy way of working, you can say, smart or lazy. It's up to you how you take it. So now I have taken this. Now what I'll do is I'll say f of I equals to. So before that, let me say display. I'll say force. Why am I doing this? I'll tell you in a moment. You will get that. I'm just displaying. This is for force 1. Okay. Similarly, force 2, it will display this one. Let me just let me see. This is I'm doing improvisation on the run. I'm not sure whether this will give any error or not. If it gives error, we will take it off. Not an issue. Okay. I'll say input. Enter force value in kilonewton. Okay. Then angle of I equals input, enter the angle in degrees, angle of inclination of force. Okay. Then now I have got this force. I will get this force from user, force 1 and force angle 1, similarly force 2, angle 2, all till n. Then as soon as I can keep adding that force to I can take its x and y components. I can resolve it along x and y. I can add it to rx and ry. So what I can do, rx equals to Rx plus f of I star cos D. What is cos D? Anybody? Do you remember? What is cos D? Yeah, cos in degrees, correct. Guru Sharan Narsamurthy sir, yeah, it could be 125 degrees, it could be 58 degrees. We are not bothered about the exact numbers here. If you can give, we can give any number, and if the code will work for any degrees or any forces. It's just this one. It could be 125 as per the diagram. So, not an issue. Then similarly, Ry equals to Ry plus, I just copy paste this whole thing. Right? So I have added these forces, and that's all I have to do in one for loop. There is nothing else that is needed from this. So at the end of this for loop, once the for loop runs from 1 to n in the increment of 1, you would see that we would have taken input from user for all the forces and their corresponding angles, and then we would have taken their components and added it to Rx and Ry, right? Resultant along x and resultant along y direction. Now the final R, okay, let me say R. I have not initiated this R anywhere, not needed. Now only I am doing it. So the final R, I can just see it as square root of Rx dot square plus, sorry, Ry square. As you people did yesterday, if I am doing any mistake while either typing or while considering, no. Okay, should I do Rx dot cap square cap 2, or I should do just Rx cap 2? What should be the thing? When do we use this dot operator? What happens if I don't use this dot here? Abhiram is saying that I should do Rx dot cap 2. Is Rx a matrix? Please see. Okay, the funda is, first of all, Rx and Ry are not matrix, they are just scalar numbers. Okay, it's a single value. Now, but the fun is, even if you do dot here, MATLAB knows that it is by mistake we have done it, and it will automatically take it as just scalar square. It won't bother much. But if there is a vector and if you simply square it, that is where it will start giving you different values or error. Okay, so here we could do dot square, or we need not do dot square. Both ways it will work fine, but it is better not to do dot square. Okay, then similarly we have we want one alpha of R, the final
Hello.
orientation. Yeah.
Hello.
Yeah. Yes, Aviram. Yes, sorry,
In this
Professor
for
Aviram.
loop, you are able to hear me, sir?
Yeah, definitely. Please go ahead.
Yeah. So it's being incremented, no, sir. Rx is equal to Rx plus f of I. So
Correct.
the Rx value is continuously changing.
Yeah, it is changing, but it is not getting appended.
I
Rx.
didn't get you, sir.
See, okay. See, f of I, this particular term. Okay, this particular term, what I've highlighted, f of I is a single value.
Huh.
It is one. It is just one number. It is equivalent to a scalar. Okay. Angle of I
Huh.
is also a scalar. even though angle and f both are vector, f of I and angle of I both are single values, just simple normal scalar.
Okay.
Okay. Then when you multiply two scalars, you're going to get one scalar only. This we already know from our, from our mechanics days, or from our this one, that when you multiply scalar, you'll obviously get one scalar only, isn't it? So the same thing holds good for here also. Just numbers. They are just numbers. F of I is one number. We will see. You'll get to know. Just give me 2 minutes. When we run this code, you'll understand the whole thing. Okay.
Okay, sir. Okay.
So Rx and Ry remain as scalar only. Even after the whole for loop runs, Rx and Ry don't change in size. They change in value. Okay, so it is like 0 equals to, or Rx equals to 0 plus some 2 into 3 or 2 into 0.3. Then Ry equals to Ry plus 2 into 0.7. Then whatever value you get, that will be that plus that. So it will just keep on adding simple numbers. Okay. Anyway, we will see. Just give me 2 minutes. You will understand. Then there is one other function, 8 and 2, which I am not sure whether people have seen. I am just to give you the idea of this 8 and 2, I am including it here. I can just do 8 and itself, but just you can explore what is this 8 and 2. I'll just give you one information. It is nothing. It is to do with obtaining theta depending on the quadrant, depending on what is the value of Ry and Rx, the sign of Ry and Rx. You will get theta in different quadrants, isn't it? So that quadrant dependent theta is given by this 8 and 2 function. D is of course in degrees. Okay, so this is the idea, right? So now let me just print this whole thing. I'll just copy paste. I'm not sure whether people have discussed the print function. I'll just show you the print function. Just I'll copy paste it because it will save some time for me. Yeah. So this is the fprintf. I think you people would have. I hope you people remember that there is something called as printf in our C programming. If at all you people have undergone a C programming course, right? So this is the same printf, but used with one prefix f, because MATLAB can print this to a file as well. And these are all format specifiers. I'm not going to deal with this too much because it will, we will lose time. We have seen even in the C programming time that it will tell what is the format of this particular output that is being shown. So this tells us that this R will be a floating point value with 4 digits and 2 decimal places. Okay, same thing for this angle as well. Okay, so let me just save this code and try to run this code here. So I'll go to this live editor here. I'll just click on run. So it is compiling, or rather it is interpreting, I should say. You should remember one thing: MATLAB is is not a compiler; it is an interpreter. So it goes one line by line. It will start executing as long as your first line starts working. First time, okay, it has come here. So enter the number of forces. So we will enter 3. Okay, then yeah, see, it encountered some error. That error is probably here. As I told you, this is not working. So I'll just comment out this thing. I just did it on the runtime, so I'm not sure, that may not work. So I'll just rerun this code. Yeah, so it is asking, okay, enter force value in kilonewton. The first force was 20 kilonewton. So let me enter 20 kilonewton. Then it is inclined at 40 degrees. Sorry, 40 degrees. Then F2 is 40, alpha 2 is 25 degrees, and F3 is 200 kilonewton. One of the participants pointed out that it cannot be 58 degree. It could be anything. This figure is just indicative. It is not necessary that the forces are exactly like that, because 25 degree won't be the angle of F2. So it is not an issue. So we will just give whatever numbers we have got, 58. So you can see here. Now I'll just show you the output. Okay, I have entered the input. Now I will just scroll down. The output f printf, you can see here. Okay, it is showing here. I'll just yeah, you can see here. Okay, so this is the output. The resultant R is 254.11 kilonewton. The angle between the resultant and x-axis is 51.68 degrees. Right. So this is the output. Very simple code. You may ask, what is the big deal here? Well, there is actually nothing big deal. It is just that we have not seen how to put it in simple code for a simple engineering mechanics problem. We can run this particular code again. We can give any number of forces now. So this code has been so written that you can take forces. So you can give some 10, 30, then 20, 30, sorry, 20, 35, 30, 40, 40, 45. You will get the output here. You can see here the output is, you can see here. So 99.62 kilonewton. Similarly, this one is 40 degrees. Okay. So like this you can, so we have created one generic code which we can run for any number of forces, right? So is this understood? Good enough? Any doubts? Have anybody? So now I think it was Professor Ajay who was asking that Rx and Ry will become vectors. You can see here, I can show you this command, this workspace window here. You can see here Rx and Ry are just simple scalar values, right? So it's okay, fine.
Sir, why that alpha R you have written there after resultant, alpha R and A tan 2D? What exactly it signifies?
8 and 2D, you can just search and find out. What this does is, if let us say for some reason Ry and Rx, any one of them, let's say Rx is negative. Okay. So if you do tan inverse of, let's say 5 by minus 3. Are you getting my point? Tan inverse of 5 by minus 3. What angle you should get?
Maybe the
Okay, let me show you here. Sorry.
yeah, the value may be in the this anything in the
See, 5 comma minus 3. Okay, 8 and D. D is nothing but degrees. Too many input arguments. Oh, wait a second, wait. I'll just. Tan. One second. Tan 2D 5 comma minus 3. Okay, see, it gives you an angle of 120 point something. Basically, minus 3 means x is, see, this is y comma x, a tan 2d. What you're getting is you can see here, a tan 2d. You can see it says y comma x. Okay, tan inverse of y by x. So now if y is positive, x is negative, it is in which quadrant? Second quadrant. So you should get an angle that is greater than 90, less than 180. But if you simply do a tan d, I don't know, some a tan d is not functioning, I'm not sure. Let me see. Just try it. A tan d is not working. A tan works. Let me see. Okay, arctan, it's saying too many arguments. Okay, let me see. Okay, let me do this. A tan d of 5 by minus 3. See, what is this giving? This is giving minus 59.03 degrees. If you just do a tan, if you just do a tan d, 5 by y by minus x, see, it gives you angle in minus, which is not the correct thing. Okay, the correct thing is it is 180 plus of this value. If you should you should add this to 180. Pi plus this is this actual correct answer. So that is what 8 and 2 gives you. You can just I don't I lose time to explain this.
Yeah,
You can
thank
just
you.
search around.
Yeah,
Huh?
yeah, thank
Okay,
you.
clear, huh? Yeah, fine, no problem. Okay, so is this fine? Okay, so let us now start with or go ahead with one more case study. So I'll just copy paste the thing. So text, I'll go to text. Anyway, for these case studies, I have not typed the code like for the previous one. It's because it's time consuming exercise. Okay, so I'll just paste the figure with this. Is it visible? I'll just save this. Sorry. So I will say engineering mechanics case study. I hope you people are able to read the problem statement. So what we have to do? There is a spike or a nail, you can say, whatever it is that is that is embedded in some object, and in front of that spiked object there is some obstruction. Okay, now you have to remove that particular spike from the object, and you apply two separate cables. You tie two separate cables to that spike and you pull it. Now the thing is, on this side, the bottom side, the force given is 500 Newton. On the top side is where we can vary the, or we have to find out what is the uh, uh, force, and the D is the range between the spike and this particular what do you say, obstruction. D will range between, as they have given you, between 1 and 20, right? So is this okay? So we have to do this. So we have to find out the magnitude of P such that the resultant T is are directed along the spike. Then what is that magnitude of T? Then plot P and T as a function of D. This is the thing that is required to be done. So now let me give you the free body diagram. Okay. So let's say solution. Okay. Too big. right? So this is the free body diagram. Okay, P and 500 kilonewton is there, and then there is a result in T. That T is not visible here. This is the resultant T. Okay, x direction, y direction, alpha and beta. We are taking this inclination as alpha. That is, P is inclined at alpha to the x direction, and 500 Newton is inclined at beta to the x direction. Okay, fine. Now, if you write the force equilibrium equations, if you sum up the forces along the x direction and y direction, you get something like this. Please cross check. Okay. Right. Now, if you solve these two equations, you will get P as 500 sine beta by sine alpha, and you will get T as something like this. Okay, correct? By the way, what is alpha and what is beta? So if you observe, alpha is nothing but tan inverse of phi by d, right? I hope you people, I'll just show you this. See, it is tan inverse of 5. Opposite is 5, adjacent is d. Tan inverse of 5 by d is alpha. Tan inverse of 7 by d is your beta. So let me just give you that as well. Okay, so these are all the formulae that are there. In fact, this is not even required. I mean, this we will not even consider it during the coding time. We already have P in terms of alpha beta, we have T in terms of alpha beta, we have alpha in terms of D. So we have everything, right? Okay. So now it's time to code this particular thing. Okay. So let me just copy paste. Very simple, very small code. In fact, and most of the things are only auxiliary thing. So I will just copy paste the code here. Vijay, what is the problem in code? Previous code is not running, is it? Did you check the? Well, you can do one thing, Mr. Vijay. You can just check for syntax, or you can just mail that particular code to either me, Devraj sir, or Tripti ma'am, and then we can check what is the error in the what. There may be some syntax error or something. Anyway, we will get ahead with this particular code. You can just check this. I am pasting it in the chat box. Okay. So I will paste one by one. The same code I will paste one by one along with the comments. I have given comments so that it is easier for reading. I am initializing or declaring one variable d, which is going from 1 to 20 in step of 1. Right? That is what this question says. You can see here range of d between 1 and 20 mm. Okay. So this is range of d. Then alpha and beta we can straight away calculate from this particular d. Just because we have the value of d, we can very easily calculate alpha and beta. Now, since d is a vector, alpha and beta will also be a vector. Now, for doing any operation with vector, you have to do this dot. You have to use this dot. If you don't use dot, what is going to happen? Okay, let us try to see this one. I'll just change this here. I'll just show this. I'll run it and show it to you. See, you can see here there is an error that has come up. I'll just see error using slash matrix dimensions must agree. Okay, you cannot simply invert a row vector. Inversion of a row vector is not possible. So you will not be able to. So that is actually a matrix operation that doesn't work. So it will give error. So you have to always do dot slash, or always in the sense in this particular case. Okay, did you understand that? Okay, then so I have to compute P. The P is very simple. It is 500 into sine beta by sine alpha. Now please observe, sine beta will be a vector. Beta is a vector. Sine beta will also be a vector. Sine alpha will also be a vector. You have to use a dot operator again to do the division between those sine beta and sine alpha. And similarly, okay, compute force T. Again, here we are multiplying two vectors. We are using the dot operator for multiplying, right? And now I'm going to plot this particular thing. They have asked for a plot in the problem, so we will plot it here. Okay, so let me run this particular code. There are few more lines which I have pasted. I will paste that here. Okay, yeah, you can see here you have got a plot. This may be very small, so I'll just explode it. If I explode, are you people seeing the exploded view? The graph is visible in the exploded view.
Yes, Narari,
Yeah.
it's a bit small. You try to pull that vertical window a little left side.
Okay, so you're not see. I have no. I exploded that graph, so it was. I clicked on this, so okay, fine, no problem. I'll just. Yeah, now you people can see.
Yeah, now it's fine.
Yeah. So this is the graph that we wanted to plot between D and T and P. Okay, but this graph is hardly understandable, isn't it? We just see some red line and a blue line with some marks. So we will have to do some conditioning or formatting of this graph. So I'll paste some of those things so you people can just observe it here. Very simple. These things you people have seen since past 2 days. So I'm not going to explain much about this. So now if I run this, yeah, now it is probably better to understand. So blue one is force P, red is the net force T. So how the distance D affects this particular both P and T can be seen from this graph, right? So that's the idea behind. So I can just click on this graph here. I think it won't show here. I have to explode it, but if I explode it, people will not be able to see it. Anyway, fine. If you click here, MATLAB shows you what is that point. Yeah, it is without clicking also it's showing. See, it is nothing but x4 comma y595.365. That's the point where both T and P are common or same rather. Okay, so this is fine. So just let me just put this CLC CL. Right? Is it okay? I have copy pasted the code. You people can check. If you are having any issues, you can let me know. Right. So let us take one more case study. an interesting one, but very, very simple one. Let me just, oh, it's already 11 o'clock. I have to rush up a little bit. So I will just, text. Okay, so this is the statement. Problem statement is that. Okay, let me just. Yeah. Right. So you are required to write a MATLAB program to plot the WL as a function of x for x ranging from 0 to 60. So this is the x distance. So how much you can load the truck such that the center of gravity of that load portion is going away from the rear wheel. That is the idea, isn't it? Nice little practical example. Very simple actually, very, very simple, nothing much. I'll just save this particular thing. So if you were to write this free body diagram for this one, it will be like this. Is it visible? Free body diagram. Okay, so you have two normal reactions at both the wheels. The center of the centroid of the truck is 500 Newton and the weight centroid is WL. Okay, now if you write the equilibrium equation, summation of force, very simple, 500 . Okay, similarly if you write moment about the rear axle, if you write moment equation about the rear axle, you will get okay, if you solve those two equations, what will you get? You will get like this, correct? Very, very simple, very simple. You just have to now write code for this particular equation or this particular expression. So let me just go to the code. Again, I'll copy paste the code here to save some time. I'll also copy paste this code on the chat window. So I have given the code for you can see here hardly some 3 lines code. The only code that matters are the 3 lines. The rest of them, they're all just extra lines, right? So this x is nothing but the vector which shows us the variation of distance between 0 to 60 mm. This one, 0 to 60 mm, right? So that particular thing you can see here. Now you can simply run this particular thing. I'll press F5. Yeah, the plot is already there with us. See, very simple. So this is how we can, even though I have taken simple examples, but the idea here is how you can formulate a given example and convert that formulated expressions into code. That's all that is there, right? So this is the idea behind the this particular example. Any doubt? Anything you want me to address here?
Narari, just check with the grid on and grid off. What are that they can do? No, just go there and check for the points. Actually, if they're able to see that points along that.
Okay, okay.
Yeah,
Yeah,
that
yeah.
you can explain.
If
Yeah,
you
that would be
just
a good option.
grid on
Yeah.
is basically grid on gives you the x and y lines along the these things. If I say grid off, okay, let me show you what happens if I say grid off. I think you people have seen this in day before yesterday's afternoon session, but anyway, just to show you. See, if I say grid off, you won't see these lines. Okay, so it becomes a little difficult to identify what is this point. Of course, I can take the mouse here and then just wait for the value to come up, like how I showed in the previous one. Okay, yeah, you can see here it will show the value here. Yeah, this is the value. Now, if grid were to be on, if the grid were to be on, it will be easier for you to identify the values. You can see here. So this we already know it is about 70 and this is about some 11 or 12 something we can see here. So it's easier to identify, right? So this is the idea of grid. Let me now take next. I have 3 more cases to be taken, so I'll just quickly move on. Now we move towards the my favorite topic, that is beams. So this is the question. Again, I am afraid I'll run short of time, so I'll try to hurry up a little bit. Please excuse me if my pace is more. Okay, so you have to write a MATLAB program to draw SFD and BMD. Okay, I'll show you the beam. Yeah, too big. Right, so this is the beam for you. Let me save this particular this one. SFD. Oh, yes, sir. Okay. Now, if we were to write the static equilibrium equations for this one, what they will be? Summation of all forces along y direction is equals to 0. So you will have RA plus RB equals to this whole force. That is, it's a UDL. Please bear with me that UDL is not pretty evidently visible, but I hope you people will understand. So it's a UDL. So 30 into 3 plus 20. So if I were to write that, so this is the equilibrium equation. Sorry. Yeah, it got pasted twice. Yeah, so this is summation of forces along y direction equals to 0, and similarly this is if you do summation of moment about A equals to 0, then you will get this particular equation. Now, I am not going to take care of the cantilever beams because they are actually easier when compared to the simply supported or overhanging beams, because in simply supported or overhanging beams, the first thing you have to do is you have to calculate the support reactions. Whereas in cantilever, we need not find out support reactions because it is known. It is a very simple thing. It is trivial in nature. So to find out these support reactions, usually when we do this for our students, when we ask how do you find out support reactions, they generally tend to manually calculate the support reactions and then start using it in the code, which is actually not to be done. I mean, it's not so smart thing to be done, because MATLAB can calculate these support reactions for you provided you have the equations. So I'll show you what you have to do. But before that, okay, let me just go to the code. So I'll go to code section. Okay, I'll say CLC clear standard step, and then I can calculate the support reaction at B first, isn't it? If you take the second equation, this equation here, I can easily calculate the support reaction at B. How do you calculate support reaction at B? It is nothing but you take 6 minus 6 RB to the right side and divide the whole equation by 6. You'll get RB equals to 30 into 3 into 3 by 2 plus 20 into 8, whole thing divided by 6. So I'll just paste that particular thing here. You can see this 30 into 3 into 3 by 2 plus 20 into 8, whole thing divided by 6. Simple. So you need not to bother to calculate by yourself. MATLAB is meant to calculate these things, isn't it? So then RA, very simple. I can just say 30 into 3 plus 20 minus RB, right? Very simple. So you can see here, I can run this particular section of code. It will automatically give me the support reactions. If you have already calculated the support reactions, you can find out. See, at A it is 60.83, at B it is 49.1667. Right? Okay. Now we have found out the support reaction. Anyway, we will use it later. Now again we will come back. Now I am sure if you remember your SOM course for this SFD BMD, we used to write expressions for this each portion, A, D, B, C. Now, of course, it might have so happened that you might have learned what is very famously or infamously called a shortcut method, like directly calculate what is value at A, directly calculate what is value at D, then at B, then at C. That sort of a shortcut method might have worked in the for the exam purposes, but for when you want to do this coding or any such thing, you require the original, the actual mathematical analytical expressions method. So here we will write expression for this AD portion, DB portion, and BC portion. So I'll just copy paste those expressions for you. Just 1 second. So for portion AD, okay, it's coming big. I don't want to waste time in minimizing them. So see, this is the force, and this is the moment expression. This I might probably try to, right? Okay, directly it has been shown as 60.833. It is nothing but RA basically, right? So what we can do now, let us, there are many ways you can do write code for this one. One very simple way, simplest thing wherein you don't have to bother about using any loop or anything is initialize 3 separate portions. Now you can see here this AD portion, the length of the beam is 0 to 3 meters. Then DB portion, length of the beam is between 3 meters to 6 meters. And BC portion, it is between 6 meters to 8 meters. So corresponding to that, I will declare 3. Okay, let me not type it out. I lose some time, so I will try to minimize the time. So I will declare, or I will use 3 separate. You can see here. So 0 to 3 linspace I'm using. I'm not using the colon operator. I'm using linspace. So start, end, number of divisions. Okay, start, end, number of divisions. Start, end, number of divisions. Okay, AD, DB, BC. You can see here AD, DB, BC. So basically I'm dividing this AD into 30 parts, DB into 30 parts, BC into 20 parts. Somewhat similar to what people would be doing in your FEM, probably, isn't it? So some similar approach I'm using here. Okay. Now, based on these expressions, you can see these expressions. So this expression I'll just now try to code it here. So I'll just write very simple. Instead of writing 60.833, I am writing RA, which is automatically 60.833 minus 30 into X times AD. Okay, that is the force equation. I will write the moment equation here itself so that you people can view it easily. Right. Okay, by the way, if you want, I will copy paste this whole code for your reference. You people can just, the code appears to be big, but it's very simple, very simplistic way of doing it without going for any for loop or anything like that. Bracket required for 30 into 3. Let me just see which bracket. I'll just come back to you. Oh, I think it did not copy paste fully. One sec. I think that is the maximum I can copy paste. So I will paste the rest of it once again. Just ignore that last line of the previous chat. This one, that one you just ignore here. This one. Okay.
Narari, you
So
can
what?
paste it in 2 parts. I think that will be good actually.
Yeah, I have done it now.
Yes.
Yeah. So 30 into 3. This one you are asking, sir? Somebody has posted. Guru Sharan Narsimurthy sir is asking bracket required for 30 star 3. In RA you are asking? It's not needed actually. It is working fine. You can see that we have got the correct answer as well. So it's okay. Okay. So this is the portion AD. Now for portion, okay, now I have to hurry up a little bit. For portion DB, oh, this is too big. Okay, so yeah, this is F and this is your moment, right? So this is moment expression, this is force expression. So for that, if I code, it will be something like this. Now the idea is, this is where you people have to understand. I will just remove this one for the time being. I will show you what happens if I don't do that, whatever I removed now. Okay, and that is the force and moment. Now for portion BC, this is the shear force and this is the expression for moment. 1 second, it will come. Yeah. Right. So that same thing, I will again code here. So I will just write this one, and similarly I'll just write this one here. Okay, so I have the FBC and MBC, force in BC portion, moment in BC portion. Now all I have to do is I have to just merge these separate vectors. I have to merge these separate vectors. Now before I merge these separate vectors, I'll just run this for your understanding. Just see, you can see here already it has populated. These calculations are done. So you have FAD, FBC, FDB, MAD, MBC, MDB, RA, RB, XAD, XBC, XDB. Sorry, right? Now let me just merge these things. Way back during the first day, second session, I had discussed this, that you can just create a new vector or a matrix just by placing the existing vectors, predefined vectors parallelly like this, right? So this gives one more row vector, this gives one more row vector. This is. Now, please observe here, if I run this code, what happens you see? Okay, if you see F, okay, you will not understand right now. If I now try to plot this, okay, if I now try to plot this SFD, this is the calculation. What I have done is I have calculated shear force for AD portion separately, DB portion separately, BC portion separately, and then I have similarly for moments I have done. I have now combined them. Now I want to plot this particular thing. I'll just show you SFD because there is one error that is going to come which I want to highlight here. Please observe. See, I am getting one error. What is that error? I will just show you 1 second. See, error using plot. Vectors must be the same length. What is this error? Please pay attention here carefully. See, XAD is how many? 30. That is the 1 cross 30. XDB is again 1 cross 30. XBC is 1 cross 20. But if you observe here, FAD, it is 1 cross 30, matches with this XAD. You see, FDB, it is just one scalar value, minus 29.167. Similarly, FBC is also one scalar value, 31.667. We needed a vector, isn't it? This XBC is a vector, but whereas FBC is not a vector. You can observe here. You can see here FBC on the right hand side workspace. It has created just one single values. Why is that so? Because if you observe this guy here, this guy is simple scalar. RA is a scalar value. 30 cross 3 is a scalar value. So I have to now convert it into the same vector as that of, let's say, DB, whatever is XDB. I have to convert it into the same this one. So what I will do to do that is I'll just multiply this by a one simple one row vector, okay, so that I get the same this one. So now you can see here, I'll just copy paste this is 20. Okay, now if I run this code again, now that error will disappear. You can see here, now you can see this is same 1 cross 20 as this one, 1 cross 20. Similarly, this is 1 cross 30. This is also 1 cross 30. 1 cross 30. Is it clear now? So now I will enlarge this particular window. 1 second. Okay. Now what does this subplot do? Any idea? I think you people got this in day before yesterday's this one. So this is a way of plotting multiple plots in the same window. Okay. So I will now plot. What I have done is I have plotted SFD. Now I will plot the BMD just below that. Now 2, 1, 1 tells that there is this tells how many rows, how many columns. Okay. So there are 2 rows, 1 column, out of which this is the first window, the first sub window you can say. Similarly, this is same 2 cross 1, 2 rows, 1 column, and this is the second sub window. So now if I run this, yeah, so this is the bending moment diagram for the shear force, for the given beam. Okay. Now you might be wondering whether this is correct or not. So for your satisfaction, let me just paste. This is a problem from one of the popular local author books. So just to show you the answer. See, you can compare. You've got the same thing. Of course, this one horizontal line that we can always get it. That's not a big issue, but that is understood, right? So this is how we can get the shear force and bending moment diagrams for a given beam. right? Okay, I have. Let me just show you one more problem. Okay, text. Oh my God. Okay. One second. Yeah, so this is the beam. This has got a step. You can see there is a bracket on top of the beam, right? So this bracket here, you can see here between the portion C and D, it introduces a moment at this particular point C, and this is carried on to this particular okay. The point C, the load is carried on. So if you write the free body diagram, it will appear something like this. Oh my God. I think I have to. Please bear with me. There's some issue with the display. Yeah. So you can see this is the beam. You will get now the standard again. I'll just copy paste this whole thing for your reference. Let me see. Oh. Oh my God. What happened? I have copy pasted, but apparently it is not come properly. Let me. So this is the reaction for or for sorry, this is the equations of equilibrium. Then let me see if it comes properly. No, it doesn't come. Okay. So this is, I will just now I will quickly, because it's already 2 minutes past 11:30. I'll just quickly give you the code for this one, how it runs, what we get. You'll get know quickly. So I will just again, I have adopted the same method for doing the work. As I told you, there could be other ways of doing this particular thing, but this is one simple way without bothering to go with any for loop or anything, without bothering to loop across the length or whatever it is. So I'll just run this for you. Yeah, you can see here. So this is the SFD BMD. I'll just enlarge this. Yeah. So this is how you get the SFD BMD. Now again, if you want to ascertain whether that is correct or not, I will just copy paste the thing here. Just you can see here. So this is the SFD BMD you get, the actual one that is given in the book. So this is how you can obtain shear force and bending moment diagrams for the various beams. All it depends on is how we are able to write the expressions correctly. It is just write the code for that. So with that, I have actually exceeded the time limit. There was one more what you can say thing that I wanted to show with respect to Morse circle. So I don't think I have time. I'll just anyway show you one. 1 second. One snapshot I'll just give you so that at least you have that idea that a Morse circle can also be plotted in a very similar fashion. Okay, this is the question you have. So wherein you have been given various cases. So I will just give you the code for this one. Run this. So you can see here, it is asking for some stresses to be given. So I'll give some random values. You can see that this is the Morse circle with okay, where is the minor principal stress, where is the major principal stress. This should actually come a little bit this side, but that's probably due to display problem. That center is somewhere here, but it is being shown somewhere to the right side. So this is what you get as the Morse circle. Okay, so with this I end today's session. Sorry for exceeding by 6 minutes. Morse circle, I'll copy paste the code definitely. I'll just copy paste the code. Anyway, you will get this whole document. Don't worry, you will get the document fully, or you don't have to bother too much.
Narati,
Yeah.
I think someone